For many years, Jeddah Tower was seen as a symbol of failure in the global construction industry. In the desert near the Red Sea, more than $20 billion seemed buried inside a silent construction site, where massive cranes stood motionless for years, while the unfinished tower gradually became a symbol of an ambition that pushed beyond realistic limits. Many people believed the project would be abandoned forever, just like many other ambitious mega projects that had collapsed in the Middle East. However, at the end of 2025, construction suddenly restarted. New floors began appearing on the skyline of Jeddah at an incredible speed, and the project that once seemed abandoned unexpectedly came back to life. So what exactly happened? Join Mandarin Tech as we explore the story behind it. Jeddah Tower was originally announced under the name Kingdom Tower during the period when Saudi Arabia began pursuing its ambition to reshape its national image beyond oil. If Dubai created Burj Khalifa as a global symbol of the modern Middle East, Saudi Arabia wanted to go even further by building the first structure in human history to surpass the 1,000-meter mark. The project was designed by Adrian Smith, the architect who also helped design Burj Khalifa, with plans for more than 150 usable floors and total investment worth tens of billions of dollars for the surrounding urban development. But the bigger the ambition, the greater the challenges became. This was no longer just about building a taller skyscraper, but about testing the true limits of modern construction engineering. And the greatest challenge of Jeddah Tower was not simply its extraordinary height, but how humans could actually build a structure like this in the harsh desert environment near the Red Sea. As skyscrapers become taller, heavier, and more complex, they face two major challenges: the enormous weight of the structure itself and the constant force of wind. With a planned height of around 167 floors and an estimated weight of nearly 900,000 tons, Jeddah Tower required a structural system carefully designed to handle a project on this massive scale. Construction officially began in 2013. However, the stability of such a gigantic tower did not begin in the sky. It began underground. Before the first floor could rise above the desert, engineers first had to solve an extremely difficult problem: how to anchor hundreds of thousands of tons of concrete and steel into the soft coastal soil near the Red Sea. The solution was the construction of more than 270 massive foundation piles drilled as deep as 110 meters underground, with some reaching stable geological layers far below the surface. This pushed foundation engineering close to its absolute limits. At the same time, the tower's location near the Red Sea created another serious challenge: corrosion caused by salt water and humidity. To fight this, engineers used high-performance concrete and specialized reinforcing steel designed to withstand salt, moisture, and extreme temperatures for decades. Once the steel reinforcement cages were placed and secured into position, the next step was pouring concrete to completely surround the steel structure, forming an enormous and stable foundation system. At that point, the foundation became strong enough to support the gigantic structure that would eventually rise above it. After the massive foundation system was completed, Jeddah Tower officially entered the construction phase of the main tower structure, also the most complex stage of the entire project. At this scale, engineers were no longer simply building a normal skyscraper, but were almost trying to construct a vertical city taller than any structure ever built in human history. To keep such a gigantic structure stable, the entire tower had to be designed with a structural system completely different from traditional skyscrapers. The base of Jeddah Tower was not designed in a normal square or circular shape, but instead used a Y-shaped design with three asymmetrical wings that gradually narrow as the tower rises higher. These wings were not only for aesthetics, but also acted as a wind load distribution system, helping break up aerodynamic vortexes that could form around the building at extreme heights. And to turn that aerodynamic design into a structure that could actually stand at such a height, the central concrete core became the most important element. This section was considered the backbone of the entire tower, containing the elevator systems, emergency staircases, and all major technical infrastructure. To construct this core as the tower continued rising higher, engineers used a hydraulic self-climbing formwork system. After each concrete pouring cycle, the entire system automatically lifted itself upward to continue building the next floor without requiring manual dismantling like traditional construction methods. This allowed the tower to continue rising floor by floor while still maintaining structural accuracy at heights of hundreds of meters. Construction teams once worked almost day and night at the Jeddah Tower site. Massive cranes continuously lifted steel, concrete, and equipment higher into the sky under the extreme heat of the Red Sea Desert. At its peak, the project was seen as a symbol of Saudi Arabia's new ambition, where thousands of workers and engineers were trying to build a tower taller than Burj Khalifa. A major turning point came in late 2017, when the tower had only reached around the 63rd floor. Saudi Arabia launched a large anti-corruption campaign, arresting and investigating hundreds of businessmen, officials, and royal family members. Among them was billionaire Prince Al-Walid bin Talal, who was closely connected to the Jeddah Tower project. After that, the project began facing serious problems involving contractors, workers, and financing. From early 2018, construction slowed down significantly. Many parts of the project were interrupted while financial pressure kept increasing. Even so, investors at the time still hoped the tower could be completed around 2020. In early 2020, the COVID-19 pandemic made the situation even worse. Global material supply chains were disrupted, labor and equipment became difficult to mobilize, and the real estate and international investment markets began to decline sharply. As a result, the construction site almost completely fell silent. Cranes stood motionless for years, while the unfinished tower remained isolated in the desert. More and more people began believing Jeddah Tower would become another failed megaproject in the Middle East, an ambition simply too large to ever be completed. After nearly half a decade of delays, it seemed that Jeddah Tower would remain nothing more than a giant unfinished concrete structure in the middle of the desert forever. However, by late 2023, the atmosphere around the project began to change when Jeddah Economic Company, the project developer, announced plans to search for new contractors to continue construction. The driving force behind this revival comes from Saudi Arabia's Vision 2030 strategy, a long-term plan aimed at diversifying the economy, reducing dependence on oil, and transforming the kingdom into a major economic, technology, and tourism hub in the region. In that context, Jeddah Tower is seen as a symbol of Saudi Arabia's ambition to reshape its global position, a demonstration of the country's engineering capability, financial power, and long-term vision on the international stage. After construction restarted, the progress of Jeddah Tower quickly attracted the attention of the global construction industry. New floors continuously began appearing on the skyline of Jeddah at a speed significantly faster than before the project was suspended. During some periods, the construction site was able to complete nearly one floor within just a few days, an extremely impressive pace for a super-tall skyscraper project of this scale. However, the higher the tower rises, the more complicated construction becomes. Strong winds, desert temperatures, and the challenge of transporting materials hundreds of meters into the air are creating enormous pressure on the entire construction site. Although the current progress is creating a lot of optimism, the exact completion date of the project still depends on funding, supply chains, and the ability to maintain construction speed over many consecutive years. According to the current plan, the project is expected to be completed around 2028. If that truly happens, Jeddah Tower will become the tallest building in the world. Inside Jeddah Tower, every infrastructure detail was designed to support the scale of a vertical city. The tower is expected to have more than 160 usable floors, including office spaces, a 5-star hotel, luxury apartments with floor-to-ceiling glass windows, a circular outdoor observation deck around 30 meters wide, as well as commercial areas and public spaces. The elevator system is one of the project's most impressive engineering features. Nearly 60 high-speed elevators are planned inside the central core using ultra-long cable systems. Some elevators are expected to reach speeds of around 36 kilometers per hour, while double-deck elevators are designed to reduce waiting times for users. Several elevators will travel directly between the ground floor and the observation deck located more than 600 meters above the ground. In addition, the base of Jeddah Tower is directly connected to the larger Jeddah Economic City development, which includes shopping centers, residential districts, underground parking, and many luxury facilities. Because of this, the project is not only aiming to become the tallest building in the world, but is also expected to function as a self-contained urban center and a symbol of Saudi Arabia's future ambitions. The next major challenge was how to transport enormous amounts of materials to a construction site located in the harsh desert environment near the Red Sea. At this scale, building the tower was no longer just an architectural project, but more like operating a massive industrial logistics network that had to function continuously for years. Every day, long convoys of heavy trucks delivered steel, concrete, glass, fuel, and mechanical equipment to the site. The project alone required hundreds of thousands of cubic meters of concrete, while many giant steel components had to be transported with near-perfect precision to avoid delaying construction. However, Saudi Arabia's desert climate made the entire process far more difficult. Summer temperatures often exceeded 40 degrees Celsius, causing concrete to lose moisture quickly and increasing the risk of structural cracking if not carefully controlled. Hot winds, sandstorms, and salty air from the Red Sea also constantly damaged machinery, vehicles, and construction materials. To deal with these conditions, materials were transported through multiple stages using heavy trucks, tower cranes, and internal construction elevators built inside the tower's core. At the same time, many construction activities were scheduled at night to reduce the impact of extreme desert heat on concrete and equipment. For Saudi Arabia, Jeddah Tower was never just a normal real estate project. From the beginning, it was seen as a symbol of the country's ambition to reshape its image in the post-oil era, as Saudi Arabia aims to become a new financial, technology, and tourism hub in the Middle East through its Vision 2030 strategy. In that context, megaprojects like Jeddah Tower, Neom, and the Line are not only infrastructure developments, but also global marketing tools designed to attract international investment and showcase Saudi Arabia's ability to pursue projects that very few countries would dare to attempt. More importantly, if completed, Jeddah Tower could become a major milestone for the global supertall construction industry. From foundation engineering and structural materials to extreme height wind-resistant systems, many technologies developed for this project could influence how humans build future megacities. And to create a structure of this scale, almost everything begins with one simple but extremely important material: cement. The massive flow of cement produced each year brings in more than $200 billion, making it one of China's core economic engines. Its scale surpasses every major economy on Earth. In just 3 years, China used more cement than the United States did during the entire 20th century, a clear sign of an infrastructure boom that few nations can keep up with. Provincial expressways, a high-speed rail network stretching over 40,000 kilometers, and megacities like Shenzhen, Pudong, and Tianjin were all built in essentially a single generation, powered by this enormous cement industry. But that speed comes at a cost. Cement plants consume nearly 8% of China's total electricity each year, release more than 820 million tons of CO2, and generate massive amounts of fine dust that put heavy pressure on the environment. Even so, to maintain its status as an infrastructure superpower, China accepts these trade-offs, treating cement as the raw fuel behind its rapid national rise. The raw materials for China's entire cement industry begin in the limestone mountains that surround its heavy industrial zones. Limestone makes up 75–80% of the raw mix and provides almost all of the CaO, the key component that determines clinker formation. To keep transportation costs as low as possible, most plants are built right next to these quarries, turning extraction into the first link of a production chain that runs around the clock. On the quarry surface, geological engineers lay out a grid of drill holes, each 8 to 12 meters deep, aligned along specific directions to create a controlled break. The holes are filled with emulsion explosives, or ANFO, along with electric detonators and stemming materials to maximize the blast's efficiency. When warning sirens sound across the site, the blast sequence is triggered, ripping apart an entire bench and producing thousands of tons of fragmented rock exactly along the planned opening line. As the dust settles, large crawler excavators move in and load the rock onto 40-60-ton haul trucks or directly onto primary conveyors leading to the plant. Oversized boulders are broken down on the spot with hydraulic breakers to prevent blockages at the crusher. At the primary crushing station, jaw crushers or hammer crushers reduce the material further, bringing everything down to under 100 mm, the ideal size for blending and fine grinding later on. Alongside limestone, clay is also mined from nearby open-pit deposits using large bucket excavators. This area doesn't require blasting, but it still needs strict control over moisture content, chemical composition, and overall consistency, because even small variations in the feed can throw the entire clinker production line out of balance. After extraction, the raw materials move immediately into a large-scale transportation system where limestone and clay are carried non-stop through a fully mechanized, closed-loop route. At many modern plants, kilometer-long conveyor belts connect the quarry directly to the industrial complex, crossing hillsides, valleys, and technical corridors without a single intermediate stop. Thanks to this continuous operation, raw materials reach the preparation station at a steady, controlled rate, significantly reducing costs and minimizing bottlenecks at the primary crushing system. In more challenging terrain, heavy-duty dump trucks still play a supporting role, feeding additional material into the main transport line to ensure an uninterrupted supply for the production process. At the processing area, the raw materials move into the homogenization system, a crucial step to stabilize the chemical composition before fine grinding. From the main conveyor, limestone and clay are fed into the dome storage at a steady, controlled rate. Inside, a stacker spreads the material in thin, arched layers, forming a perfectly layered pile across the entire floor. On the opposite side, a reclaimer moves smoothly along the pile, recovering the material in the same order it was laid down. This layer-by-layer stacking and reclaiming method evens out variations between quarry batches and ensures a consistent, uniform feed for the production line. The blending process begins as each homogenized raw material is pulled into the automated dosing system, where belt scales continuously measure and adjust the proportions according to the plant's design formula. Once the mix meets the required ratios, it is sent directly to the grinding unit, the most energy-intensive stage of the entire line, and the step that ultimately determines the quality of the raw meal before it enters the preheater tower. Depending on the plant's technology, the material is fed into either a vertical roller mill or a multi-compartment ball mill, massive machines capable of continuous operation and handling anywhere from 100 to 500 tons per hour. Inside the grinding chamber, the intense compressive forces and friction from the rollers or steel balls break the material down to particles smaller than 90 microns, producing raw meal with a high level of uniformity. Some older production lines still use the wet grinding method, adding water to create a slurry. This approach makes chemical control easier, but consumes significantly more energy, so it is gradually being phased out in favor of more efficient dry grinding systems. Throughout the entire process, all operating parameters, including feed ratios, grinding speed, fineness, and gas temperature, are monitored in real time by the SCADA system to ensure the raw meal remains stable and consistent before moving on to the next stage. Heat from the hot gas flow spreads through the preheater tower, but the raw material must follow its own path before entering the harshest stage, the rotary kiln. From the top of the tower, the limestone clay mix drops through tall cyclone chambers, spiraling with the rising hot air. Each cyclone works like a natural heater, raising the temperature of every particle to around 850 degrees C within seconds. In the calciner, the heart of the tower, carbonates break down almost completely, turning the raw meal into minerals ready for high-temperature reactions. This multi-stage structure operates like a vertical river of material, weaving through steel chambers and absorbing energy from the burners below. Coal was once the main fuel, But to cut costs and emissions, many modern plants now add alternative fuels. Shredded rubber from old tires, cleaned of metal and ground into chips, is injected into the burner, burning fiercely at nearly 1,000 degrees and providing similar energy to coal with far less CO2. The entire process is tightly controlled by automation. Material drop rate, airflow pressure, and cyclone temperature are all kept at optimal levels to prevent over- or underheating. Even though the material moves quickly, every step aims for two goals: delivering a consistent feed to the kiln and reducing environmental impact. It's how China's cement plants balance massive output with growing pressure to green the industry, a clear sign of the country's infrastructure ambitions. The deep rumble of the rotary kiln mixes with the glow of the red-hot flame, creating a steady industrial rhythm. Inside the long steel tube, raw meal from the preheater drops in and slowly slides along the refractory lining, turning with the slight tilt of the kiln. As it moves into the hottest zone, each grain of limestone and clay is exposed to more than 1,100 degrees, where their original structure begins to break down and reorganize into new minerals. At this temperature, CaCO3 rapidly decomposes, releasing CO2 and forming highly reactive CaO. The CaO then combines with silicates and illuminates in the mix to produce the key clinker phases: elite for early strength, belite for long-term strength, and illuminate for setting behavior. This is the most critical stage of the entire process, where even small fluctuations in temperature or retention time can cause underburned or overburned clinker. To keep conditions stable, the control system constantly monitors kiln speed, fuel flow, and gas pressure using heat sensors and infrared cameras. The burners inject fuel in a swirling pattern, creating a long, penetrating flame that transfers heat deep into the material bed. Hot gases from the decomposition reaction are drawn out at the kiln inlet, carrying most of the CO2, while excess heat is recovered and sent back to the preheater. Along the kiln, the material gradually fuses into glowing red clinker nodules, rolling steadily along the kiln axis in the constant roar of fire and steel. The red-hot glow still clings to each clinker as they slide out of the rotary kiln, their constant movement carrying them straight into the cooling system. On the moving grate, powerful blasts of cold air are pushed upward from below, taming the intense heat that's still well over 1,200 degrees. Each clinker slowly changes color as it cools, sending waves of heat rising in steady pulses. The haze of warm air mixes with the fading red light, creating a vivid scene where heat and mechanical motion blend together in the process of stabilizing the clinker's mineral structure. The residual heat from the cooling process still clings to each clinker as they slide into the high-capacity grinding mill, processing several hundred tons per day. Here, the clinker mixes with about 3 or 5% gypsum and mineral additives, such as fly ash or ground granulated blast furnace slag. Under continuous pressure and friction from steel balls or rotating rollers, the mixture gradually breaks down into fine cement powder with a fineness of around 4,500 cm. Fine dust rises into the air, and the reflected light on the machinery creates a scene that feels both mechanical and alive. Automated dosing systems and sensors monitor every batch, ensuring consistent mineral composition, fineness, and strength, transforming the solid clinker into the refined foundation of high-quality cement. The fine cement powder drops into the intermediate silo, flowing with a steady rhythm like a small river inside the plant. An automatic sampling system extracts a portion of the powder and sends it to the laboratory, where advanced sensors and analyzers record key parameters: fineness, moisture, mineral composition, and strength development. Each value is continuously compared with internal standards and national specifications, ensuring every batch leaving the plant remains completely uniform and stable, a place where mechanics and precision meet in a seamless, almost living rhythm. The uniform cement powder flows from the silo into the packing area, where the rhythm of the plant is defined by a continuous stream of material. Each empty bag is positioned under the filling nozzle, and precisely 50 kilograms of cement drop in, thanks to a modern dosing and weighing system. The automatic packing line runs smoothly, producing 500-600 bags per hour, creating a scene that feels both mechanical and alive. The sound of falling powder blending with the reflections of light on the metal surfaces. At advanced plants, robots fully replace manual labor, guiding bags into place, filling them, sealing them with heat or tight stitching, and ensuring accuracy in both weight and closure. The filled bags move down the conveyor, where sensors monitor each one, removing any that fall outside the required specifications. Next, robotic arms stack the bags onto pallets with brick-like precision, 40 bags per pallet. As the load is shrink-wrapped, the warehouse lights reflect off the surface of each bag, forming a refined industrial scene where machinery, automation, and precision move in perfect harmony, completing the final step before the product leaves the factory. As it leaves the automated warehouse, the cement is transported to concrete batching plants, where it joins its familiar companions: fine sand, crushed stone, and clean water. Automated dosing and mixing systems adjust every percentage with precision, ensuring each batch of concrete reaches perfect uniformity. Within minutes, the seemingly simple gray mixture becomes a foundational material ready to support massive structures. From river-spanning bridges stretching thousands of meters to skyscrapers and expressways worth billions of yuan, every concrete element carries the imprint of advanced engineering, automation, and strict quality control. The sounds of mixers, conveyors, and concrete trucks blend with the rotation of tower cranes, creating a rhythmic industrial symphony. Every grain of sand and every piece of aggregate is monitored for weight and size. Even roller vibrations and slight temperature changes are recorded to guarantee structural stability for centuries. In this vast landscape, concrete is more than just a material. It is a symbol of technical strength and modern infrastructure, present across China's trillion yuan megaprojects, where technology and labor come together to build greatness. From these refined materials, cement becomes a solid foundation behind modern, massive structures. Every bag of cement and every batch of concrete carries precision, technology, and mechanical rhythm, contributing to the construction of bridges, highways, skyscrapers, and trillion yuan projects across China. This process is not just a story about materials, it's a testament to the blend of labor, engineering, and automation, where quality and performance are carefully controlled at every step. If you found this journey fascinating, be sure to like and follow Mandarin Tech to explore more engineering and infrastructure wonders from around the world.